All right, this last example is a very tricky one. This is definitely one that is, if it's one it's hard for you, that makes sense, and that's okay. This is definitely a tough example. There's a lot of geometry and a lot of derivation necessary. So a cylindrical tank of radius r and length l is lying horizontally, as in this picture. It's filled with oil to a height of h. So distance from the bottom upward is h. And then we're given some more concrete information. Suppose the radius is 1.5 meters, its length is 10 meters, and that the tank is filled with a constant rate of 0.6 cubic meters per minute. So let's go ahead and just parse all this information. So what is known? So known information is that r is 1.5, and I like fractions, so I'm going to write 1.5 as a fraction. We know L is 10. We also know that the tank is being filled, so that means the rate of change of the volume of oil is going to be 0.6, which is 3/5 as a fraction. And so that's our given information. And our goal is to figure out the rate of change of the height when the height is exactly 0.5 or 1/2 as a fraction. So our first goal here is, since we are given the rate of volume, we somehow need to come up with a formula that represents the volume here of oil in this tank. So the volume of this section. Well, the easiest way to find the volume of something, especially something that has its cross-sectional area is the same. For instance, we can think of let's think of a regular cylinder like this. If we imagine just slicing the cylinder with a plane here, we're going to get this little cross-sectional circle. And no matter where we slice this cylinder, no matter how low or how high we slice this cylinder, we're always going to get the same size circle. The area of all these circles is the same. So if in one direction, let's say up or down vertically, all the cross-sectional circles are the same, then the way to figure out the volume of the cylinder is to just take one of those circles, let's say its area is pi r squared, and then we want to multiply it by this distance, h. And that's precisely why the volume of a cylinder is pi r squared, that's the area of the cross-sectional circle, times the height. We can effectively think of taking the area and stretching it by a distance h. So it seems, since the cross-sectional area of oil in this tank is always the same shape, right here, no matter where we slice it, we have the same shape, the same size even, we really just need to figure out the area of this cross-sectional area and then multiply that by L. So our goal really right now, our immediate goal, is to find the area of that. Okay, in order to do this, there's a couple little things we have to do. The way that I'm going to ultimately think about finding this area is I'm going to first find the area of this entire sector. So I'm going to find the area of this full thing, because we can imagine splitting it, right? So if I take this full area, I'm going to call that AS for the area of a sector of a circle. And if we subtract from this area here, which I'm just going to call the area of the, I guess we'll go ahead and call this the area of a triangle. For reasons that will become obvious soon, I'm going to call this 2AT, because really, if we think about it, the way we're going to find the area of this big triangle is we're first going to find the area of one of these triangles, and then we're going to double it. So I'm going to just call this 2AT for now. So the area, so double this triangle plus the area of that triangle. If we do that, then when we subtract them, what we're going to be left over with here is just the area underneath. That's it. Okay, so that's our goal. So we ultimately are going to do the following. We are going to, let's go ahead and set ourselves up for success. Let's say, we need a lot of room, so we're going to come over here. Let A of S be the area of a sector of a circle of angular width let's see here. How big should we make this? Well, if we're thinking ahead, ultimately, since I did just mention that we're going to need to know the area of those two smaller triangles, let's go ahead and call this angle theta and this angle also theta. They have to be equal. So then the area of this full sector, the angular width, then would be 2 theta. This would be a 2 theta sector. So angular width 2 theta. There we are. So then to figure out this, we can use proportionality. We know that the area, so this circle has radius capital R. So the area of a full circle is pi times this radius squared. And the full area would have to correspond to the full angular measurement, which would be all the way around, which would be 2 pi radians. So this must be equal to, well, this is proportional, so we would have to take the area of the sector that we're looking for, so this portion, A sub s, and divide it by its angular width, which is 2 theta. Solving for the area of the sector, A sub s, we will have theta r squared after we cancel and simplify. So now we know the area of the sector is theta r squared. Now, to get the area of a triangle, so let A of t be the area of one of the two triangles. So again, we'll draw a circle. And we know that the radius is r. What else do we know? Well, if we think about it, this distance right here, do this in blue, this distance is h. So that means this distance right here must be r minus h. So then for one of these triangles, if we just pull out the one triangle and blow it up a little bit, it's a right angle. This is theta. Then this has to be r. This is r minus h. Now we need to know what this side length is right here. Well, Pythagorean theorem, this would be the square root of the hypotenuse squared minus the other leg squared. And if we go through simplifying and expanding, collecting like terms, we're going to have r squared minus 2hr plus h squared. But then that minus will allow us to cancel those r's, and we'll get 2hr minus h squared. So this will be the square root of 2h capital R minus h squared. So now the area of this triangle is 1/2 the base, which is this square root term we just figured out, times the height, which is going to be r minus h. Now, the area that we're looking for, so let A be the cross-sectional area of the oil in the tank. In this case, A is, what did we say before? It's going to be the area of the sector minus the area of that double triangle. So triangle 1 times triangle 2, so this would be A sub S, area of the sector, minus 2 of those side-by-side triangles. So the 2 here will cancel with the 1/2 here, and we will get something that looks like the following. Pi r squared minus, I'm going to write the r minus h first. That way we don't try to confuse or think that it's also underneath the square root when it's not. Okay. Now here's the thing. We have expressed the cross-sectional area A in terms of theta, r, and h. Now r is a constant, so that's fine, but theta is actually going to be a variable, because if we think about this, as we fill in with additional oil, then the oil level is going to rise, in which case this angle theta is going to get bigger. So theta is variable, and of course the the oil level h is also variable. So effectively we have A expressed as a function of 2 variables. We want to reduce this down so that it's a function of 1 variable. So since there are multiple h's making an appearance, it would probably be easier to just eliminate this one theta. So can we somehow express theta in terms of other known things? We can. What we can do is take a look again at this triangle. We could use the fact that we know, let's look at the adjacent and hypotenuse sides, since they're simpler than looking at, for instance, this and the opposite. The square root, we don't really want to have more square roots than we need. So the easiest thing here would be to think of cosine. SOHCAHTOA. The cosine of theta is equal to the adjacent side length over the hypotenuse side length. And of course, if we really wanted to, we could write this as 1 minus h over r. To solve for theta, we can go ahead and do the inverse cosine of 1 minus h over r. So then the area is now a function of one variable. So this would be cosine inverse, arc cosine, in other words, of 1 minus h over r times r squared, so that's right here, minus r minus h times r square root. All right. And now, ultimately, we wanted an expression for the volume. And now, since we know the cross-sectional area, we can just multiply this expression for the area by the length L. So this would be L times all of this stuff. So there's our expression for the volume. That is a lot. Now what we're going to do, let's go ahead and give ourselves some room here. Let's just move this up here. If you're following along in the previous video, we definitely did not even bother with part B. Whoops, that's okay. So let's just section this off and start from there. Start from the top. So ultimately, we want to go ahead and take our derivative, dv dt. dv dt, L is a constant, so L will just stay there. We'll differentiate the interior. Remember that the derivative of inverse cosine of x is going to be negative 1 over the square root of 1 minus x squared. So this is a chain rule, though, because we have an inside function. So this will be negative 1 over the square root of 1 minus the entire inside, so 1 minus h over r quantity squared. But then we have to do the chain rule, multiply by the derivative of the inside, which is going to be negative 1 over r dh dt. With that, we've got another r squared. That's a constant, so that just stays there. Minus, now we do have a product rule because this has an h and this has an h. So derivative of the first would be negative 1 times dh dt, so negative dh dt, times the second, left alone, 2hr minus h squared, square root of that, plus the first term, so plus negative r minus h, times, remember that we can always treat this as as just parentheses to the 1/2. So this chain rule would be times 1/2, leave the inside alone, times the derivative of the inside, which is going to be 2r dh dt minus 2h dh dt. Running out of room here. Close parentheses, close brackets. Okay. This, thankfully, dramatically cleans up. So here we've got double negatives. That's good. And furthermore, let's think about this square root. So this square root, let's just look at the inside for a second. The inside's this. Well, what we could do here is remember that r minus h over r, we just rewrote that to get 1 minus h over r because maybe we thought it was easier, but honestly I think it might be nicer to square it like this. So if we square it like that by doing that replacement back to what it originally was, we'll have the bottoms being squared, so r squared. The top, we have to FOIL that, so that would be capital R squared minus 2hr plus h squared. And then we need a common denominator here, so we could make this an r over r, which would then give us, let's see here, this would be r minus r squared plus 2hr minus h squared all over, my common denominator, this is an r squared, so my apologies, this should have been r squared over r squared, which should make this an r squared. That looks better. All of that those two things cancel, and we're left with 2hr minus h squared all over r squared. Now that's what this entire square root in the bottom turns into. So it's really like we have 1 over the square root of this, 2hr minus h squared all over r squared. Which we really don't need the full square root, just only on the top, because we can take a square root of r squared. So with that, we are dividing by a fraction, so that's multiplication by the reciprocal, so this is no different than r over the square root of 2hr minus h squared. All right. So, collecting things here, we've got double negative, so we're going to have a positive here. This square root we figured out is just this. So then notice here that the r in the bottom will cancel with the r in the top. So this really is just 1 over the square root of 2hr minus h squared times another r squared, which this r squared, right? Don't forget about that. We can just put that in the top. And then we have dh dt. That's a lot of simplification, but there we go. Plus, because we've got double negative here, I've got this square root. And now notice here that this exact same square root is what's in the bottom here. So if we want to add these two together, we could get a common denominator by multiplying this by that same square root. So if we do this square root times this square root, that will just give us itself, the inside of the square root, all over the bottom of the square root. dh dt. Now here, notice that there is a 2 in common that can be factored out. That would cancel with this 1/2. So that's good. And then what would be left over? So it looks like we have a minus here. This is really a square root in the denominator, so that's even in common still, which is awesome. But then we have this r minus h. And what's left over here? We factor out this 2. So if we, in this term here, if we've taken out the 2 already, then we have dh dt times r minus h dh dt. We factor out the 2 and canceled it already, so that's why we're not talking about those 2's. If we factor out the dh dt, we're just going to be left over with r minus h dh dt. So we get another copy of this, so we can just say this is squared times dh dt. Close brackets. All right, continuing. L times, well, really, doesn't even seem like we need brackets. It's just L times some big fraction times dh dt. We have an r squared plus 2hr minus h squared. Our fraction might need to be even bigger. Now we have to subtract this expression FOILed out, so let's go ahead and do that. So this is negative r squared minus 2hr plus h squared. So this is negative r squared positive 2hr minus h squared. So this would be negative r squared positive 2hr minus h squared. All that would be over our common denominator of the square root of 2hr minus h squared. dh dt. Now stuff's going to cancel. The h squareds cancel. The r squareds cancel. Oh, sorry, the h squareds do not cancel. Only the r squareds cancel. But we do have what appears to be 2 times 2hr minus h squared. So dv dt is equal to 2 times L times 2hr minus h squared all over the square root of 2hr minus h squared dh dt. And fun fact, if you have the square root of something, so if you have something divided by the square root of that same thing, this is just equal to the square root upstairs. It works the other way around too. If we have a square root of a over a, we could just write this as like that. You can derive this using laws of exponents, right? This would be a to the 1 over a to the 1/2, which would be a to the 1 minus 1/2, which is just a to the 1/2. So we just get that. I think the second thing I wrote was incorrect. That's why I wanted to go through that really quickly. If I have square root of a over a, this should just be equal to, let's see, this would be a to the 1/2 minus 1, which would be a to the negative 1/2. Yes, I wrote that incorrectly the first time. Should have been just that. So this turns into 2L square root 2HR minus h squared dh dt dv dt. Now that's a lot of algebra. After all of that, where are we? Well, we can fill in our known information. We know that dv dt is going to be 3/5. So we're going to have 3/5. Oops, I guess I'll do this down here. 3/5 equals 2 times 10, the length of the tank, square root of 2 times a height of 1/2, radius of 1.5, so 3/2, minus 3/2 squared, which is 9/4 dh dt. If you go ahead and simplify all of that and solve, you'll get 3 over 50 square roots of 5 meters per minute. This is certainly a huge exercise in algebra.